Wiener processes and Ito's lemma. So first, we are going to discuss about this concept today. Stock prices jiggle around constantly, up a little, down a little, in way that look almost completely random. So how do you build serious math on top of something that looks like a pure noise? The answer is a tool originally built to describe coolant particles bouncing randomly in the water. And it turns out to be exactly what finance needed to describe stock price too. I will show you that Wiener processes and why it matters and how a rule can called Ito's lemma let you actually do useful maths with it. No heavy notation required. What is random motion really? Let's start with the picture in your head. Imagine a tiny particle floated in water, getting bumped randomly from every direction by surrounding molecules. It has no memory. Where it goes next has nothing to do with where it be. This is called Brownian motion. It is called Brownian motion, first studied by botanist Robert Brown and later explained mathematically, notably by Einstein. A Wiener process is the precise mathematical version of this random wandering. It has a few defined features. It starts at zero. Each little step is random with no bias up or down. Steps don't depend on each other, no memory of the past. Over any stretch of time, the total wandering goes, but in an unpredictable, jagged way, not a smooth line. If you plotted it, it would look like a jittery, zigzagging path, never smooth, never predictable, step to step. Why finance borrowed this idea? Here, the leap that made this so useful for market stock price movement, especially over very short time period, look a lot like the same kind of random pattern. Nobody can reliably predict whether a stock goes up or down in the next second, minute, or a day. The moment look essentially random, much like that jittery particles. So financial modeling borrowed the wider processes as a building block and added one adjustment. Real stock price also tend to drift upward over time. Companies grow, economics expand, and have a certain typical size of daily jiggle called volatility. So stock price movement is equal to a steady drift upward plus random noise modeled by a Wiener process. That combination, drift plus randomness, became the foundation of most classical financial model, including optional pricing. The problem with ordinary calculus here, whether it get genuinely interesting in ordinary calculus, if you know how a variable changes over time, you can use standard rules to figure out how anything based on that variable changes to. But a Wiener process breaks those ordinary rules. Why? Because it is so jagged and irregular that are key assumptions in behind normal calculus. That thing change smoothly simply doesn't hold. The randomness doesn't average out the way ordinary calculus expects. This created a real problem for every quantitative finance if the stock price follow this jagged random process. How do you mathematically describe how something derived from the stock price, like an options value, changes over time? This is exactly the gap that Ito's lemma was built to close. What Ito's lemma actually does, named after mathematician Kyoshi Ito's, Ito's lemma is essentially a specialized version of the chain rule from calculus. but adapted specifically from processes that include this kind of randomness. If you know how some random underlying variables like a stock price behaves, Hito's lemma tells you precisely how anything mathematically derived from it, like a options value which depends on a stock price, behaves too. Here, the key insight it captures that ordinary calculus misses because of how randomness compounds in a Wiener process and exact adjustment terms show up related to the volatility of the process that would appear in normal calculus at all. In other words, Ito's lemma is not just calculus, but slower it reveals that randomness is not contribute an extra measurable effect on how derived quantities behave, an effect that vanished if there is no randomness at all, but which matters enormously where there is. Why this matters for option pricing? Here, why all of it is not just an abstract math trivia. It's a literal foundation of modern option pricing. Remember, an option value depends on the stock price, and the stock price is modeled using a Wiener process to figure out precisely how the option value evolves over time, which is exactly what you need to price it correctly. You need a mathematical tool that work with randomness. That tool is Ito's lemma. It's the key step that let learners translate the stock follow is random process into here a precise equation describe how the options price behaves, which is exactly the foundation the famous Black-Scholes option pricing formula was built on. Without Ito's lemma, there is no rigorous way to bridge random stock movements and a formula for value of something like a option derived from the stock.